Hey, this is Dr. B here yet again, and let's talk about enthalpy. That means heat change at constant pressure. This can be a convenient method and a realistic method for measuring uh, energy changes. Oftentimes, when they happen out in the world, things don't pressurize. They're in an open system. That's why we choose enthalpy, which is the term H, compared to heat, which is the term Q. The change in that energy, or heat in this case, gives us the delta sign, right? The change in enthalpy. This would mean the change in enthalpy for a reaction. This may be done using a calorimeter. So it's pretty simple. If you're dealing with enthalpy versus heat, enthalpy means the pressure will be constant, Q means not necessarily so. Let's apply this to a couple of actual chemical reactions. And before we do, let's consider the fact that a heat change might be in the negative or the positive direction. If it's releasing heat to the surroundings, we call that exothermic. And by convention, we give that a negative value. If it's requiring heat, we call that endothermic, and we give that a positive value. Okay, let's observe ice melting. Wow, that is so cool. You sit there for an hour and an ice cube turns into a puddle of water. Only a scientist could get excited about it. We did a calculation in the previous slide that shows that this would require, if you had a cup of water, an 18-gram size cube, that would take 6,010 joules. Fine. Well, how do we know that? Well, it's 334 joules per gram. That's the enthalpy of fusion of water. Fine. Let's, in this case, it's releasing heat to the surroundings, by the way, since it's a downhill process going from ice to liquid water. Let's write down what's happening in terms of a thermochemical equation. Now, take a look at that for a second and tell me what you think of that chemical process. Aha! Did anybody say it's not? Well, that's the thing. A thermochemical equation does not have to be a chemical process. We're just melting water. That's just physical. There is no chemical reaction occurring. But there it is. It required 6,010 joules. Since there's 1,000 joules in a kilojoule, that's 6.01 kilojoules per mole. Is that true? It actually is. And that's another reason why we chose 18 grams. By the way, that's a lot less than a cup. I mentioned earlier that was a cup. 18 grams is way less than a cup. But fine, that's 18 grams is a mole of water. H2O, 2 plus 16. Now let's solve a problem. The combustion of 1 mole of methane is a different thing, and we're not melting it, we're burning it. It releases 8,904 joules of heat. A chemical engineer would probably use these kind of numbers on a regular basis. Let's write that thermochemical reaction. So we're burning methane. That means it's combining with oxygen. We've memorized at some point that when we burn hydrocarbons, they make carbon dioxide and water. We balance it and we get a 1 to 2 to 1 to 2 ratio. We add our little energy thing, and that's what makes it a thermochemical equation. Let's take a second, and this is going to make solving this problem so much easier. That's per mole of methane. So let's convert it to grams. It might just give us a nice visceral understanding here. 16 grams of methane, that's 12 plus 4, when it reacts with 32, but 2 of them, right? Each mole is 32 grams, but we got 2 of them. 16 grams of this plus 64 grams of this better make 80 grams of these things. That's 44 plus the 36, that's 18. Wonderful. So to make 36 grams of water, hint, hint, it's going to require 89, it will release 8,904 joules. Now they say how much energy is released during the formation, not of 36 grams, but of 12 grams of water. Can you see how you might already know the answer? Right? If it's 36 grams, it's that. 12 grams is going to be a third. It's going to be a little under 3 kilojoules, right? Boom, we're done. But let's also solve it mathematically. How so? Let's start with what we're given, and that would be the 12 grams of water. And we know that that is 2/3 of a mole, and we know that every 2 moles, because it's given here, it releases 8,904 kilojoules. You could put the negative sign there if it makes you happy, but I always tell my students, just say whether you're releasing or producing. I mean, that's more realistic anyhow. So That's fine. So how much energy is released? 2,968 joules. It would sound funny, would it not, to say, hey, we've released a negative 2,968 joules. No, 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 no. You want to just talk about it normally rather than use the sign, at least in my opinion. But that's the value. Does it make sense? Yes, because it's a third of what was shown there. That's an introduction to enthalpy.